think we're starting.
Yeah.
Girls, you are live. Go, go, go.
Yes, go, go, go. Hi, everyone. This is Sam from WBA ING Amsterdam, and I'm the event manager for this tribe. And today we are having the first YouTube presentation, and we've got three amazing speakers. And let me introduce you, Jessie.
Yeah, so my name is Jessie. I work as a community builder at ING Analytics. And together, actually, the WBAA tribe and ING Analytics host this data science community. And we are very excited for this edition. First time live streaming from YouTube. And we have very nice speakers, three amazing talks from our own data scientists located in different countries. So we're very happy about that.
We would like to thank from our heart our colleague Julian Legrand-Lambert, who is the developer and community builder for ING Tech, which without him, we will not be able to be here and live with you guys. So one important thing I need to mention, there will be a 15 seconds delays on the chat. And make sure that if you do have some questions, please write them in the chat and then Jessie and myself will read them. But let me first kick it off by introducing our first amazing speaker, which is called Daniel Timbrell. And he is based in Amsterdam, and he's working for a very nice team for ING, which is called the Financial Risk team. And some news about his life is that he moved 2 years ago in the Netherlands after married his beautiful wife, and is working with the risk and pricing advanced analytic chapter. And before then, he completed his PhD in mathematical technology at the University College London. And thank God, in his free times, he loves to play chess and play piano. And his presentation, it's quite difficult for me to say, but I'll try to make it. It's called Perturbation Dangers in Explainability Models. So there you go, Daniel.
Yeah, that's perfect. I hope you can hear me. Give me a nod if you can hear me. Yes, perfect. All right, then I can get started. So thanks everyone for tuning in. I have no idea how many people are there, so it's just me speaking into a void at the moment. But thanks a lot. So basically, as Samantha just said, I've been working for ING Risk and Pricing for about just over 2 years now. Now, instead of giving a presentation where I talk about a particular project that we've recently been working on, instead, I just want to present a few cool ideas that I've seen regarding using perturbations in explainability models. So the outline of this talk is essentially, firstly, we're going to take a look at just a really simple machine learning classifier, looking at where we can and cannot trust this model. We're then going to take a brief sidestep to looking at feature importance. More specifically, we're going to take a look at the feature importance methods, or common feature importance methods that involve manipulating the data in some way. We're then going to combine these first two topics and see essentially when what happens when we start to sort of break correlations within the data, how much can we then actually trust these models that we've built. And then we're going to end the talk with looking at some fundamental LIME and SHAP packages, which are really gaining popularity right now, but how we can actually use perturbations in the data to completely fool them. So without further ado, brings me to my first main slide. So imagine a really simple machine learning classification problem. So we're trying to find, and these are the first two objects that just came to the top of my head, classifying nice little cute penguins or bassoons, right? So you've got essentially here, really simple data set. You've got mystery feature number 1, mystery feature number 2. These range from about -3 to 3 on both axes. And you can see that the gray dots are these. So these are the penguins. And the orange ones are the bassoons with some, let's say, decision boundary between these located around here. So that's all very well and good. Fit, predict the model, fine, sorted. But then imagine you come across, let's say, more test data, maybe production data, something like this, that looks like this. So what am I showing you here? So everything contained in this black box is what we've seen in this slide here. So now all we've essentially done is massively expand both of the axes for mystery feature 1 and mystery feature 2. And so a question that we really need to ask ourselves is how much can you trust what the model says? So each color here is now the model predictions. So the model says, hey, all the way down here, these are penguins, and all the way up here, these are bassoons. But can we trust anything that the model says about this? I mean, you can argue possibly that as you get closer and closer towards the black box, that the model becomes a bit more reliable. But even then, how much is it even reliable around this part? Because it has never seen this part of the data. Now, for a discussion on how to deal with models being highly certain around regions they've never seen, I really recommend checking out this video. Here, however, we're going to be focusing on what happens when you use these model extrapolations, because that's what they're doing in these regions, these extrapolations for explainability purposes. So more explicitly, looking at feature importance methods that involve interacting with the data that then leads to regions that you've never seen. So this leads me into looking at some of these feature importance methods. So we can start with permutation importance methods. So this, as far as I can tell, the first source of this is from this machine learning textbook. And this is the one that scikit-learn uses as well, the one that it implements. And the idea is pretty simple. So essentially for each feature, so you go through feature by feature of your data set D, you keep all the columns the same, except this feature, and you randomly shuffle up this feature. So as a really simple example for our mystery feature 1 and mystery feature 2, what you can do is if you permute on mystery feature number 1, this means you keep mystery feature 2 constant here, and you just shuffle this up. Now, I've drawn arrows that show it going step by step, but of course, it doesn't have to be like this. You can just shuffle it up like a deck of cards. And the idea is that you now take what is called your corrupted data set, you put it into your model, and you see how the model performance changes over time with this. And now the idea is that simply if the predictions of the model or the accuracy of the model now dramatically reduces, then mystery feature 1 was really important for the underlying data distribution. And similarly, if you were, for example, to shuffle mystery feature 2 and it has no effect, the idea then is that, okay, how this wasn't really that important for the underlying data distribution at all. As you do this for all of your features, and the idea is that you see how important they are. A similar feature importance method that is used in the ELI5, so explain like I'm 5 package, is to just instead replace this column with just random noise. Now, of course, there's different ways that you can replace data in your data set per feature. So for example, the same things that you use for, let's say, missing value imputations, you can fill with the means, fill with the medians, and so on. But it's all roughly the same idea. So here you go through and again, replace feature by feature with just random noise, see how much this affects your model score as you do this. So now we're going to take a look at actually the sort of ramifications of this, of permutations or replacing them with missing values. We're going to stick with permutations here, but also replacing with random noise or something also applies to what I'm about to say. So imagine we've got now these dots, and what we're going to do is we're going to permute this gray dot on mystery feature number 2. So this means that mystery feature number 1 is just going to stay constant, but now this point is going to essentially steal its mystery feature number 2 value from another one of these orange dots right here. So it means it will either move up or down. And in this case, you pick a random one, and in this case, it's moved down. So it was here, and now it's here. So that's all well and good. Now, a question that you have to ask yourself here is how, can this point essentially belong to the original data distribution? Now, there's all sorts of different things that you can calculate for this. You can calculate different statistical measures, so things like the Hellinger distance or Kullback-Leibler divergence, or just simple t-tests. But I think no one watching would find it overly controversial if I did something quite unscientific here, which I do not advocate doing for the validation, but just by eyeballing this point and just say, okay, it's basically with these clumps of orange dots, fair enough, it could probably be part of the underlying data distribution. It's not overly controversial to say that. But now what happens if I have instead some correlated data? So here, I forget the exact correlation parameter I used to generate this data, but obviously you can tell it's a pretty strong correlation. And so what we're going to do is again permute on this value for mystery feature number 2, meaning it will go either up or down. And let's say we permute and it moves here. And now we ask ourselves again the same question: can this point belong to the underlying data distribution? I think people would now find this much more controversial to say, if we were to just unequivocally say, yeah, sure, no problem, this is part of it, because obviously this really doesn't seem to be following the underlying trend. But this is just one point. And so what happens now if we do all of them? So we've permuted every feature, not every feature, sorry, every dot here on mystery feature number 2. And you see there's some overlap for these points in the middle. So this looks okay. These could belong to the underlying distributions. But then we've got regions around here that the model has never seen, but we're asking its opinion on this. We've got regions over here that the model has never looked at. So essentially, if I just go back real quick, we are essentially in this situation here, where we're now looking at these model predictions in regions that the model has never seen. So you're essentially asking this model to really just extrapolate based on this. And so now, instead of this sort of semi-fun idea of mystery features and bassoons and penguins, let's go for a more concrete example. So let's replace mystery feature 1 with height, and then let's replace mystery feature 2 with a correlated feature. So let's say weight, all right? And instead of bassoons and penguins, let's say we're trying to predict whether someone is on a professional basketball team or not. Now, if you're not careful, you can end in quite a sort of silly scenario with these permutations where, for example, the model may say, I can deal less with, let's say, 2-meter tall people who weigh 10 kilograms over here than I can, for example, with 200-kilogram babies, something like this. Now, as facetious as that sounds, if you're not careful, you can sort of end up in these scenarios. So therefore, your model says, okay, I can deal more easily with these really, really heavy babies. Therefore, weight is more important to classify whether or not someone is part of a basketball team or not, which is clearly very silly. Now, correlations are within data at the best of times a thorny issue. So you can see, for example, when you look at random forests, how they generally calculate feature importances, they have been shown to either really overweight or really underweight particular features by doing this. But I really want to show that using some of these other methods, you can really run into other risks doing this. And this actually brings me to the first paper that I want to show called, and I love the name of this, by the way, the Please Stop Permuting Features. Gets quite straight to the point. And I really advocate that if you have any correlations within your data, if you're using any permutation methods for generating your feature importances, I really recommend checking out this paper. Now, for a discussion, usually a presentation, I know you're not supposed to just read text off a slide to your audience. However, I think this quote here is quite important enough and sums up essentially what I've been saying for the last few minutes. So in permuting only one of the correlated features, we break its relationship with the remaining correlated features. And this results in evaluations of the function in regions which have no data nearby. Now, they actually go further in this paper. And so what they do is they generate a really simple underlying distribution, that's this y, based on 10 independent normal distribution variables, normally distributed variables. So here, we can tell just by immediately eyeballing this, right, that if we were to use some feature importance methods here, you would expect features 1 through 5 to have, they should have roughly the same importance because they've got the same coefficient. Similarly, you would expect feature number 6 to have basically no importance because it's just a 0. And then 9 and 10 should be the largest, while 7 and 8 should be, close to the bottom. And that is indeed what you find when you look at cases where there's no correlations. The most important ones in this left side graph to look at are, in my opinion, the red lines and the green lines. So these are your random forests, is the green, and your neural nets that are fitted on this for the reds. However, what happens is that they then generate the same data set, but have X1 and X2 with a 90% correlation. What does this mean? Well, we then essentially end up in the same situation that we were before, where we break these the correlation patterns when using the permutation feature importance. And really crucially, what happens is that features number 1 and 2 are seen as more important than all of the other features, which should not be the case. But again, it's because you're asking your models to extrapolate into these regions that they've never seen. So what can we actually do about this? So one thing that we can do is to permute your data and then relearn the model. So in this way, what you're doing is you're not asking your model to give its opinion on a data space that it's never actually seen. Although, of course, this does involve retraining a model probably a lot of times because you probably don't want to trust just one permutation. You probably want to do it a whole bunch of times, which means rerunning a whole bunch of models. Another example that you could use is conditioning and relearning. So here you permute your data set, but only within groups of observations. So you still try and preserve some correlation structure. And I believe this also relates to this fast leave one feature out method, which also permutes on groups of features. So if I just quickly go back, it would, for example, well, one example would be to allow permutations, for example, here, where your data points are overlapping and they could belong to the same distributions, but to then not allow this region here and not allow these regions here. I think a really important one to consider are these really simple examples, the LOCO, otherwise known as LOFO, so leave one covariate or feature out. And this is just where you discard feature by feature, rerun your model, check the new accuracy, and see how important this is. So importantly, these methods remove the overimportance of correlated features like the X1 and X2 that we saw. The only sort of downside here, which is the trade-off, is that they're computationally expensive because you're having to rebuild some more models. So now we've now basically seen how certain correlations or perturbations within the data can sort of trick us unintentionally without us realizing it. We're now going to look at how we can actually use perturbations of the data to deliberately fool other people, most notably with the SHAP and LIME packages, so how we can fool these packages. So imagine you've built a pretty complicated neural net like this one that I've just stolen from the internet. And imagine, well, here what they're doing is it seems they're predicting essentially a chemical reaction based on some image that they have. So that's fine. Imagine you've built this big neural net. It's got loads of layers. I think regardless of your neural net experience, you would have a hard time really describing exactly how your model is doing what it's doing for all of this, especially if with each layer that you're adding, it just gets so much more complicated. So you've essentially got this black box. And of course, when you want to take your model to production and so on, you really need to describe what it is that this model is actually doing. So your goal is to describe this f of x, where x is, of course, your underlying data sets, your images in this case. And so essentially, your goal here is to explain this function. Now, recently, there's become more and more popular packages such as SHAP and LIME, which are used to explain this. And what they do is that they learn an explanation model of X. Now, what you don't want is you do not want your explanation model being as complicated or as black boxy as your f of x. Because in this case, all you're doing is using a black box to explain a black box. And then you essentially get this infinite regress where you never really explain the first black box that you built. So you also have this complexity parameter that you need to take into account. And so essentially what you want to do is firstly, you want f and g as similar as possible. So g is basically doing what f is doing, but at the same time with a reduction as far as you can in this complexity parameter. So that's essentially how these packages work. But what now if we try to write a biased model? So for example, a purely sexist model or a purely racist model, and still be able to make LIME and SHAP think that it is fair. So this is a super interesting paper that I really recommend reading. Now, of course, before I go any further than this, obviously I do not advocate that you do this. I really just want to highlight the fact that LIME and SHAP are not infallible, and reading this paper and seeing how you can actually fool these techniques really helps you understand how these models can be gamed, essentially. So now assume that there is a dastardly man with a dastardly plan. That's this guy here. And his goal is to essentially deploy a model that is, let's just say, incredibly sexist. And this is going to be used for a critical decision. So I work in a bank, so let's pick a financial example. Let's say he's running a model that uses purely sex to determine whether or not someone can get a loan. So women are not allowed loans and only men are. Now, what this guy needs to do is, with your model validation, you have to provide often black box access to the customers and regulators. And they're probably going to use some of the more sophisticated packages to try and figure out how exactly this model is working, such as Shapley and LIME. And so his goal here is to fool these methods, the Shapley and LIME, to hide f of x. So even if you use Shapley and LIME, you look at it and you go, yep, seems absolutely fine to me, put this into production. How do you do that? So firstly, there are two models that you want to focus on. Firstly, we build our completely biased model that just takes, let's say, race or sex as the feature. And then we do what we're actually supposed to do, which is build the unbiased model in the first place. Now what you want to do is you actually want to take your original data set and begin perturbing it to give it a separate label. So you take your original data set, you give it a label of 0, and then you, for example, with your perturbations, you can take your original data set and permute some of the features, as we saw previously, or you can replace with random noise, or just noise some of the features and so on, as we also saw previously. And we assign these a label of 1, and you now write what's called an out of distribution classifier to try and see whether a model, a classifier, can tell whether the data belongs to the underlying distribution or not. And then you package this all up into something called an adversarial classifier. So why do you do this? So the entire point of this model is that once Shapley and LIME are used on your data set, they begin often to perturb or permute some of the data. And that's where this out of distribution classifier comes in. It will essentially realize that the data is being played with. Essentially, it thinks it's being attacked, and its sort of defense mechanism, if you want to think about it like that, is to release or deploy this unbiased model. Then once it thinks it's in production, it thinks it's seeing normal day-to-day data, it will then release the biased model. Now, just to make you aware, because of the delay, I'm going to finish in about 1 minute. So please start writing some of the questions that you have in the comments. And as far as I understand it, I will get those at the end. So basically, also in this paper, what they show is as your out of distribution classifier becomes, let's say it starts really bad. So you look at this, the race as the top feature here instead of sex. So your out of distribution classifier is really bad. This means you're always deploying your biased model because it cannot tell the difference between perturbed data and non-perturbed data. But you can see, and it's much more prominent in the LIME package here, there's a point beyond which your LIME package cannot pick up the fact that you have released a completely biased model now. And it's the same with Shapley, albeit a bit more complicated. There essentially becomes a point where you are now being able to detect differences within the data to such a strong degree that you know when LIME and Shapley are being implemented. And so you can essentially fool the people using LIME or SHAP. So just before I say thanks for listening, just to conclude, basically what we've seen is that certain correlations in the data can really cause damage if you're just blindly accepting whatever feature importance methods you're using just tell you and not questioning exactly what it is that you're doing. And then in these cases, we've seen some methods. I really do recommend checking out the LOFO or FLOFO methods to overcome this, essentially, or to write some models to essentially use some techniques to overcome this. And so basically also be careful using any perturbation techniques when explaining your models, because even things such as LIME and Shapley, the fact that they use perturbations of the data, these can also be fooled. Now, I think these slides are going to be shared out afterwards. If not, just get in touch with me. I've put some further reading, some really interesting papers. Trying to basically papers regarding writing models in production and things like this for explainability purposes. Possibly some problems within Shapley packages and things like this, which I think are pretty cool. And I've also listed all the packages mentioned in this talk if you want to check those out. But that is basically it. Please do get in touch with me if you've got any questions, anything like that. Send me some spam, and that is it. Thank you very much for listening. And now if I go back here.
So thanks a lot, Daniel.
Thank you, Daniel.
So we got actually one question in the chat, but we are not sure. I think there was one question, which hours webinar this, but I think until what time this takes. So in total, we are having talks for 1.5 hours. So for 4:30, we're done. So I have another question from Thomas. He's asking, hey, Dan, would you know of any ways to recognize when adversarial is used as a black box?
Yeah, it's really interesting. I'm not sure. I really know that I think in the future, what we're going to really see is that there probably will be need for some sort of more adversarially robust methods for this to essentially stop this. I don't know how you would write one of those off the top of my head, but I think this is going to be the sort of next level of feature explainability models. But how to actually know whether an adversarial thing is being used, I guess, I don't know, maybe eventually there's going to be sort of one person trying to use an adversarial to detect whether an adversarial is being used in a sort of battle between them, but I'm not exactly sure.
Okay, thanks. Thomas, I hope this answers your question. Another question from Yehun Kim. He says, thanks for the nice talk. Do you think it will be helpful if we rely on sophisticated permutation, depending on covariance and relying on the data generative distribution for permutation?
Yeah, I think so. I think basically if you were to use some, let's say, more sophisticated, where you really do pay attention to exactly what your perturbations or permutations are doing to the data, then it's okay. But if you're just, let's say, blindly using them just to go, yep, this is clearly the most important feature, then you can really run into issues. But like I say, with some of the other ones where you allow permutations within particular groups and things like this, then you should be fine. I believe, but it's essentially, yeah, it's more like just using it without really questioning exactly what you're asking your model, where you get the problems.
Okay.
Thank you.
Yeah, so thank you. These were all the questions. People are saying thanks a lot for your talk. Great talk. So thanks again.
Thanks a lot.
So I think that was for Daniel. So now we're going to the second talk. Santiago, he will give the second talk for this meetup. So we're very excited because he's working in our ING Madrid hub. So that's one of the analytics hub we have at ING. So it's the first time we have someone from abroad. So Santiago, welcome. So I will tell you a little bit more about Santiago himself and about the topic. So Santiago will talk about the multi-label supervised classification problem. So during this session, you will become familiar with this multi-label paradigm, and you will review the most used algorithms to solve these kind of problems. Something about Santiago, he has a background in computer science and artificial intelligence. And in 2018, he started with his PhD in artificial intelligence. And his main research interests are primarily in the areas of machine learning, data mining, probabilistic graphical models, and multi-label classification. So thanks again, Santiago, for joining us. We are very excited and enjoy the talk.
Thank you, Jesse, for the introduction, and good afternoon, everyone. Thank you for joining our online data science meetup at ING. The topic of this second talk today is about multi-label classification, which is a topic I'm familiar with because of my PhD. And actually, I would like to thank my supervisor, Professor Pedro Larrañaga, for sharing some of the material I present today. So today we will introduce to multi-label classification. We will see what kind of algorithms we can find in the literature that allow us to solve multi-label classification. And also we will review some software and data sets so that you all can start your own learning path and keep practicing with this multi-label paradigm. And yeah, this is the main goal, that you all acquire new knowledge, but also consolidate it. So after the 20 minutes of this presentation, we'll have a 10-minute session of question and answer. So please feel free to share your questions in the chat, and I'll be glad to answer all of them at the end. Okay, so let's start with some overview and basics of what kind of algorithms we can find in the literature and what really multi-label means. Here you have a comparison between a classification problem that involves single label data at the top of the screen and multi-label data at the bottom. You can see that we all are used to work with this single label case in which we have just one single class variable to be predicted based on the values of some feature variables x1, x2, x3, etc. Here we could measure the correlations between the features and the class variable to finally search for the best classification model, for example, which could be a random forest, logistic regression, neural network, etc. In multi-level classification, instead, we have multiple class variables to be predicted at the same time, which in addition usually present correlations between them and not only with the feature variables. You can see that traditional machine learning algorithms, those we just named, cannot deal with this kind of problems with multiple class variables at the same time. So we will see in the coming slides what kind of algorithms are proposed in the literature. Okay, one more comment in this slide I'd like to make clear. I've taken this graph here in the top right corner from a publication has been accepted in the Artificial Intelligence Review journal. You can see the relationships between the different paradigms of classification. So for example, binary classification would be this example in the left, when we have one class variable to be predicted with two possible values. Multi-class, I'm sure you'll have heard it as well, is when we have, again, only one class variable to be predicted, but with multiple possible values. Both binary and multi-class can be referred to as one-dimensional classification, since only one class variable is to be predicted. Multi-level classification is this example below in this slide, such that we have multiple class variables and all of them being binary with two possible values. Each class variable is seen as a label. That's why the name of multi-label classification. And each label can be present or absent with a value of 1 and 0 respectively. Multi-dimensional classification is a more general classification problem, and you can think in it as a combination of multi-class and multi-label problems, because it involves multiple class variables with multiple possible values for each of them. So today we will focus on multi-label classification, which is a simpler version of multi-dimensional classification, but it is much more popular. So yeah, multi-level classification problems come about in numerous application domains, and it has been a hot topic in machine learning literature during recent years. For example, in terms of image understanding, we all know the popular binary classification problem about classifying an image as a cat or not a cat. From the multi-level perspective, we can enrich this problem by predicting the presence or absence of more than one object. This is having multiple values in labels, instead of just one. For example, here in this example, the label grass is present in the 3 images, but the label cow is only present in the first one. This is a good example also for you to show that correlations between labels are common in multi-label problems. For example, if the label airplane is present, as it's happening in the 3rd image, I can think that the label sky will also be present with high probability. More examples of applications are shown here, such as demographic classification, and you will find many more in the literature, since, as I say, multi-level classification is a very popular topic during recent years. A bit more of basics. You may find multi-level classification with 3 different notations, but all of them meaning a similar thing. The first one, regarding class variables, is the one we all are familiar with. Here, multi-level classification is about finding a function h that assigns a vector of d class values to each vector of m feature variables. And this is each class variable c sub 1, c sub 2, etc. is predicted with a value. Here in multi-level with a 1 or with a 0, since a label can only be present or absent. The labels notation, this second one, assigns a subset of present labels to the vector of feature values. This is those that have a 1 from the class variables notation are the labels that are assigned to the vector of features. As you can see, the meaning of both notations is the same, but just wanted to mention it for you to know that you can find different ways of defining a multi-level classification problem in the literature. Okay, and there is a third notation, the ranking one, which is slightly different. Here, the output of the classification problem is a ranking among the labels. We have that the present labels from the other notations will have the highest ranks in the ranking, and the absent labels will have the last positions in the ranking. For example, for this first data case, a possible ranking could be first the label 1, since it's present, second the label 4, because it's again present, third the label 2, because it's absent for that example, and fourth the label 3. Some of you will have already realized that assessing the performance of a multi-label classifier needs a different approach to that from the single label case. Here in multi-level classification, we are predicting multiple values at the same time. So measuring how well we are doing should consider the performance of all the class variables predictions and not just a single one. You can find multiple evaluation metrics in the literature. Here I'm just sharing a compilation I made for both multi-level and multidimensional problems. You can see we have some metrics when our prediction is a hard classification. This is when the labels are present or absent. We are just giving a 1 or a 0. We also have metrics when our prediction is a probabilistic classification. This is how probable is each label to be present or absent. And finally, other metrics when our prediction is a ranking among the labels. This third notation we just saw in the previous slide. Without going into too much detail, let's just see the two most used metrics in the literature. The 0-1 subset accuracy can be seen as an extension of the traditional accuracy. It's going to have a value of 1 when an example is correctly classified in all labels and a 0 when not, no matter if just a single label was misclassified. The Hamming loss, instead, is much less strict since it measures how many labels are being misclassified. Of course, there are more complex metrics available in the literature, but yeah, just wanted to show the two most used. And let's move on to the core of the presentation, to the algorithms that allow to perform multi-level classification. Tsumakas in 2009 categorized the algorithms in two groups: problem transformation on the left and algorithm adaptation on the right, you can see. Since these two types of algorithms address the classification in a different way. The problem transformation, on the one hand, transform the multi-level classification problem into one or more single-level classification problems. And each of these sub-problems are solved with traditional models, such as random forest, Bayesian networks, whatever you want to learn there. The algorithm adaptation methods, instead, extend a specific classification algorithm to directly deal with multi-level data. I let you hear some references to specific single-level classifiers that were extended to multi-level classification. And you can see they were published in really well-known journals and conferences. Today, we will focus on the first group, the problem transformation methods. Since these algorithms have a common thread and it results easier for you to get an overview. Nevertheless, I'll also present the extension of Bayesian networks as an example of algorithm adaptation. So let's go then with the problem transformation methods. The first one, it's called binary relevance, is the simplest method. Basically, it just transforms the multi-label problem into as many single-label problems as labels. For each of the labels, it's going to learn one binary classifier, independently of the rest of the labels. Then the relationships between labels are not going to be considered. As I said, this is the simplest method, so let's see how we can improve it. This algorithm, called ranking by pairwise comparison, learns a binary classifier for each pair of labels. This is label 1 versus label 2, 1 versus 3, 1 versus 4, 2 versus 3, etc. Each model is going to predict which label of the two is preferred. Then each model is trained with examples that have present one of the labels, but not both. For example, this first model is trained with examples that have label 1, this is X1 and X3, and those that have label 2. This is X4, but not both of them. And for example, X5 is excluded since both labels are equally preferred and it's giving no information to this particular model. Okay, so at the end, each model is going to give a vote to any of the two labels, the one that is preferred, and the votes of all models are summed, such that we have a ranking of preference between the labels, as you can see here in the bottom of the slide. In this example, the label 3 received all possible votes and has the highest rank. And the label 2 instead didn't receive any vote and occupies the last position in the ranking. As you can see, no hard classification is achieved, but yeah, there are some techniques in the literature that allow you to threshold this ranking and have a final bipartition of the ranking into present and absent labels, into positive and negative labels. Okay, the next method does perform a classification, a hard classification. We are going to know which labels are present for any of the examples. It's called calibrated label ranking, and it is a combination of the previous two. It's going to learn both those models from binary relevance on the top, as many as labels, and those from the ranking by pairwise comparison method on the second row, as many as pairs of labels. Again, each model is giving a vote to one of the two labels. For binary relevance models, although we only have one label to give a vote, it's like we are adding a virtual label, lambda sub 0, which is going to be later used as a splitting point between present labels and absent labels. So at the end, we have again a ranking among the labels and also a hard classification, as I told you. For example, label 3 and label 1 score higher than the virtual label, and that's why they are the ones that are finally classified as positive labels. In addition, we know that the label 3 was preferred to label 1 in case that we just want to give the most preferred label. Okay, let's move to the next classifier. It's called classifier chains, and its extended version, ensembles of classifier chains. This method learns again as many binary models as labels, and each model is going to predict the present of each label. The trick here is that this learning process is done as it was a chain, such that the predictions from previous models are taken as extra feature variables for the next models in the chain. Then relationships between labels are somehow taken into account. However, you can think that this method is dependent to the order of the chain you choose, and you may obtain different results with different orders of the class variables in the chain. And also models that are placed at the end of the chain may result in less accurate predictions because you are concatenating this error in the predictions of the previous models. That's why an ensemble version of this method was also proposed, which uses several orders of the chain, and at the end, the predictions are averaged of all the models in the ensemble. Okay, label power set is a really naive method, again, like the label power set, like the binary relevance one, sorry. And actually, they both are considered the simplest ones that give rise to smarter multi-label classifiers. Here in label power set, each possible combination of present and absence of labels is annotated as a different class value in a new multi-class classification problem. Then we have all possible values, which are 000, 001, 010, 011, etc. It has, as you can imagine, two main drawbacks. The complexity is exponential in the number of labels, as it will have too many class values, which in addition, extremely few training examples for some of them. And also, this method is unable to predict label configurations that do not appear in the set of model that was trained with. For example, in this example, if the combination 1111 is not available in the training set, then this method won't be able to give a prediction of this value. So there are some models that try to improve the limitations of this label power set. The first one is the prune sets and its ensemble version again. Here, those label sets, this label set is a combination of labels that rarely occur are prune, and they are reintroduced along with subset of the label sets. In this example, the label sets of labels 3 and 4 is prune since only 2 total cases exist in the dataset. At the same time, those cases are reintroduced in the dataset along with label sets of label 4, this fourth example in the training set. Instead, the label set of labels 2 and 3, this third one, is not a subset of label 3 and label 4 because label 2 is not included in the original label set. So thanks to this method, we have reduced the complexity of label power set since not all possible combinations are to be predicted, but we still are unable to generalize to configurations not appearing in the training set. By using, again, an ensemble version of this model, we can avoid this limitation of generalizing to unseen combination of label sets. An ensemble of prune sets is going to create as many data sets as models to be part of the ensemble by using sampling techniques. For example, bootstrap, let's say. For each sample data set, a prune set model is going to be learned. Then each prune set model predicts the most probable label set, then giving a vote to the labels present in this label set that it's predicting. Again, the votes are summed for all the models, and a ranking of presence among the labels is achieved. If we want to pass to a hard classification, we just have to apply a thresholding method, and we will know which labels are present, are positive, and which ones are absent. We have another algorithm that it's called random k-level set, also RAKL in the literature. While the ensemble of prune sets we have just seen selects the label sets with sampling techniques, this RAKL method selects them at random. Then it's going to create n models. In this example, n is equal to 6, to solve simple subproblems of label sets of size k. In this example, k is equal to 3. Each model is a label power set, the one that models all possible label combinations 0001 that we just saw in 2 slides ago. And now the number of labels of these subproblems that label power set is modeling is highly reduced. That's why label power set now does make sense. Again, each model of the ensemble is going to predict the most probable label set, of course, only of those labels that the model works with. For example, this first model H1 is only going to predict if label 1, label 2, and label 8 are present or absent. In this example, only label 1 and label 8 were present, so both of them are going to receive a vote. And the votes are going to be summed along all the models. We have, again, a ranking of present, of popularity between the labels. And if we want to apply a threshold value, we can have which of those labels at the top of the ranking are actually present. As you would expect, the greater the number of votes per label is, the higher the effectiveness of the RAKL method. The number of models n and the size of the label sets k are proportional to the number of expected votes per label. At the same time, we don't want them to be too big. Otherwise, the complexity of RAKL method will increase. It's suggested in the literature to use k equal to 3 and n equals to twice the number of labels in order to have 6 expected votes for each label. Okay, the models we have reviewed are the most frequent ones that you can find in the literature. If you start browsing the literature, you will find many more multi-level classifiers. For example, this one called Homer that converts the multi-level problem in smaller subproblems in a hierarchical way. Okay, let's move on to the second block of group of algorithms, which are the algorithm adaptation. Here we are going to be quicker. This is the multidimensional Bayesian network classifier, or MBC in short, which extends traditional Bayesian network classifiers to directly deal with multi-label data. Those that are familiar with Bayesian networks will know that this model encodes the conditional independencies between triplets of variables in this directed acyclic graph structure. Without going into too much detail, the change here in the multi-level paradigm is that we are creating as many nodes in the Bayesian network as class variables we want to predict, instead of just one node as it happens in the single label case. Then we can distinguish these 3 different subgraphs of the MBC. The class subgraph is going to model the dependencies between the class variables. The breadth subgraph represents dependencies between class and feature variables. And the feature subgraph models, models dependencies between the features of our problem. Also, this last slide, this is an extension of MBC's classifiers. This is a paper I published 2 years ago. Basically, you can see that this method places general MVCs in the leaf nodes of a classification tree, and an internal node is a feature variable that has as many children nodes as the possible values of the associated feature. And new samples are going to be classified with the corresponding MVC leaf in relation to the values of the feature variables that make up the internal nodes. Okay, almost the end. I wanted now to share with you some data and software you can find in the literature so that you all can start playing with them and consolidating the information we have been presented today. In this link, in Cometa ugiant.s datasets, you will find a lot of benchmark datasets with different size in terms of data, in terms of number of features and number of labels. And actually, some of these datasets are used in the literature for comparing different multi-level classifiers and those that you are proposing as new in the literature. Regarding software, you have available libraries in R, Python, Java, and I think there is also one in MATLAB. The Python library is a scikit base, which is really nice. The one I've used most is the R one, which is very complete. You can see that we are talking about recent work, 2018, 2019. And should you want to explore a bit more the literature, I recommend you these two nice up-to-date papers, which reflect they are two reviews that basically show the most important information of multi-level data. And just to finish, some code from the R library, just for you to see that what we have presented today is what you can find in the literature. Sorry. For example, here in this slide, we are reading a multi-level dataset called birds, with the goal of predicting what birds are singing based on some acoustic features. Each bird is then a label, which is going to be present if the given bird is singing and absent if it's not. As you can see here, just with this call that is circled in orange and blue, we are learning a binary relevance multi-level algorithm with a random forest as base classifier. This library offers many multi-level classifiers, not only this one. And for example, all those we have seen today are available in this library. You can see here binary relevance, ranking by pairwise comparison. I'm following the order here. Calibrated label ranking, classifier chains, ensemble of classifier chains, label power set, prune sets, ensemble of prune sets, Rakel and Homer, all those we have seen today. Also, different base classifiers are available. For example, random forest, naive base, support vector machine, but also random majority base classifiers predict respectively random values and the majority value of all labels, which is really helpful if we want to compare our best algorithm after tuning it with these naive models that they should work worse than our tuned algorithm. So we have reached the end of the presentation. Hope you have enjoyed it, and also hope you can start browsing the literature. You'll see there are many papers with many sites, since multi-level has been a hot topic in machine learning during recent years. And hope you can start identifying multi-level problems in your business and giving them a solution based on data. So thanks for your attention. It has been a pleasure. Yeah, it's time for some questions now.
Thank you, Santiago. You did excellent. There were some people who were asking us if we can share your presentation later, which I do believe we can. If people will give us their email address, then I will forward your presentation, also the presentation of Daniel, and also the next presentation that we will present. I see we do have a question from Dan, who is saying, is the R implementation more sophisticated than Python?
So we have 4 possible programming languages, which are Python, R, Java, and MATLAB. I think MATLAB, you are not going to be interested in it. Yeah, I would recommend you the Python one or the R one.
Okay. Thank you, Santiago. And the next question is, what's the SOTA and multi-label classification for tabular data?
Thank you, Manuel, for the question. For tabular data, the state of the art, I would say that Rakel, the random k-level sets classifier, is the one that performs the best, or in general the best. But yeah, as you know, in machine learning, there is a theorem, the no freelance theorem, that says that no single learning algorithm is going to perform the best one in all possible types of data sets. So yeah, what I can suggest you is you just to learn all the models, just tune them, and let's see which one is performing the best one for your specific data.
Thank you, Santiago. Another question from Francisco Javier, who is asking, what do you think is the most successful algo in multi-level problems?
Okay, so the same question again. I would suggest you Rakel. It's the one that it's giving me the best results so far, but it really depends on your data. So I would suggest you to train all the models that are available in these libraries, making hyperparameter tuning, and yeah, you will be able to find the algorithm that best works for you.
Okay, great. Thank you. So if there are not any more questions, can we go to the next presenter, which is one of our colleagues from our UK office, but is from the WBA team here in Amsterdam, and Thomas Sostak, and you will hear about model performance. So his presentation is called Population Shift Monitoring Made Easy, the Popmon package. So you will hear about model performance, and the team has developed a generic package that would allow monitoring data like population stabilities over time. In this talk, our Thomas will present the motivation and challenge of data monitoring, as well as possible solution to it. Few notes about Thomas. Thomas is a very young data scientist, sorry, and he's working for the Holzerbeck Advanced Analytic for the past years, and his team has been working on developing an advanced population monitoring package. And Thomas has a double degree in data science, and in the past years has been running a co-founded web solution agency for more than 5 years. So there you go, Thomas, good luck.
Good luck.
Thank you, thank you. I hope you can see this. Yeah, so hello everyone once again, and greetings from London. Thanks for amazing introduction, and also thanks Daniel and Santiago for great presentations. I really enjoyed listening to it, and I think my presentation was well introduced by Daniel, who described also some data shifts problems in his presentation. And yeah, it's my pleasure to have you all here, and thanks for the invitation for all organizational team. So I would like to present Popmon, something that we have developed internally at ING, and it was very useful for us. Therefore, we would love to share this with the community. As you can already imagine, Popmon stands for population monitoring, and population shift monitoring could be also called as a covariate shift problem, which looks into data shift problem, which I'll elaborate in this presentation. So first, for words about me. Sam already introduced me, but I'll just give a brief introduction. So I'm a data scientist at ING, namely Wholesale Bank Advanced Analytics. I've been at ING for 1.5 years, and the first half of the career I've been focusing on the data shift monitoring problem. And as an outcome of this, we have developed a package, which we have open sourced recently in April. So if you have any questions or any feedback after the presentation, feel free to reach out to me. And here you can also see the presentation outline. We're going to talk about motivation, why we started this, and the problems we have bumped into our solution. We're going to jump into demo and show the use case within ING that we use this on. So initially at ING, we have observed that our models, our machine learning models and data were not being monitored carefully enough. And after looking into open source solutions available, we didn't find anything that would completely suit our needs. And since we had some past experience in doing this right, we have decided why not to do it ourselves and build something suitable for our needs. And why is this important is because we want to run reliable and consistent models in production. We want to be sure that newly incoming data and predictions are consistent with the trained data on which model has been trained and tested initially. Because if input features change over time, then we cannot guarantee that test performance will be the same as intended. And also it's good for reporting purposes. So for example, for audit, if anyone's going to check your data quality, how it was a year ago, it's always good to have a paper trail of this and keep a log of your data quality, especially if you work in such a regulated industry as banking. Some common issues that can be seen when working with data are population shift, data rot, and time dependencies. So population shift is when features are changing over time. So feature distributions, for example, as we'll see also later. Also data rot, so when model is being trained on the one data, but it's not relevant anymore for the predictions. So basically, the data changes over time, and the previous data becomes irrelevant for the new model anymore. Also, the time dependencies. So, for example, you can observe that some data is seasonal. So, for example, you have spikes in data at the end of the month, and you would like maybe to take this into consideration when training your model. Yeah, so when building a solution, we have identified 3 types of monitoring, namely data, predictions, and model performance monitoring. So if we look at the open source community now currently, there are quite some solutions for model performance monitoring, namely Seldon and MLflow. However, if you look at the data and predictions monitoring, it's quite lacking. Those 2 solutions are providing some kind of data monitoring. However, it's not sufficient because they're tracking only mean and standard deviation of the data. And let me show you why is that not enough, just tracking those basic profiles of the data. So if you look at this plot here, if you look specifically at the data points, you can see that data points are moving over time. However, if you look only at the data profile, you see that the mean and standard deviation, which is here represented in this box plot, are not changing over time. If you look at the histogram, which represents the distribution of this data, you can obviously see that it's very different. It differs a lot over time. So if you would be tracking only mean and standard deviation in this way, you wouldn't be able to see the change in data. Another example is if you look at the 2D data, you can see that the mean and standard deviation for both axes doesn't change. However, if we look at the histograms of the same data, you can see that it changes quite a lot. So if we would be tracking only those basic statistics, we wouldn't see basically a data shift in this case. So histograms help here a lot. And another good example is, for example, if our trained data has one distribution, which you can see here in blue, we build model on this, and then we want to basically predict a new incoming data, which in this case is test data. If we apply exactly the same model on the test data, it's probably not going to perform as we have expected because the distribution is completely different. And this is fine if you look at this. It's fine to inspect it visually because in this case we have 1 or 2 dimensions. But imagine if you have way more dimensions and you have a lot of features to take into account. So you would like probably to have this. You would like to detect these shifts automatically, and then all of these of these features at once, or even better to have it scheduled somewhere and be done automatically, and you would just get alerts once in a while if your data is not behaving as expected. So we have developed a Popmon package for this, and I'll just explain very briefly how it works in a very generic way. So we have incoming data, which is here represented as new data. It's a raw data, could be CSV, pandas, whatever. You convert this data into histograms, And ideally, which in this case is test data, so your incoming data, and ideally you would have a reference data, which is your train data, and you would compare how this incoming data, how similar it is, or like how does the distribution compares to the train or reference data. And based on that, you compute a bunch of metrics with statistical comparison methods. And based on thresholds that you impose, you basically would like to alert if your neural data is much more different from the reference or trained data. Yeah, you don't necessarily have to have reference data. You could also compare to the incoming data. So to for example, the same incoming data, test data. If you have data coming, for example, in a batch of 1 year, for example, you could split the same data per week or per specific period, let's say per month. And you could compare data to itself. So let's say each week you would compare to the previous week. So in this case, we split 1 year into 52 weeks. And we take consequent weeks. So like week 1, week 2, we can see that distributions are quite different. If we overlay them on top of each other, we can see that even better. And then we can visually see that those histograms are different, but we, as I already explained before, we would like to have it to be done in a more automatic way. And how do we measure this difference? How do we make it more tangible? So we apply a bunch of statistical tests. So in this case, chi-squared, Kolmogorov-Smirnov, Pearson's correlation. We have much more tests, and with the help of Popmon package, you can implement your own tests very easily because you have an interface of histograms, and basically you can apply any of your favorite tests on those histograms on the data you get. And also, yeah, we get the same data profiles if you're interested in described before, the mean standard deviation and the others. And you would ask why histograms? Why do we use histograms? Histograms are very useful because it keeps aggregated information. So we don't keep any raw data, which is very good for data privacy and confidentiality. So yeah, we don't have any raw data, so we don't get in trouble with the privacy issues. Also, it's good because size is more minimal, so it's easier to store. And also light for sending over APIs. So let's say you want to have a client and the server, for example, running Popmon on server. It's way easier just to aggregate this data into histograms on the client side and send it over the API. You don't have to send gigabytes of data. Way easier and way faster. And also, once again, you avoid data privacy issues. Also, monitoring works identically with both big and small data because if you have more data rows, which is basically is being aggregated in the bin counts, you don't get many more rows if you would be storing, for example, a table. And also, histograms are more visual, so it adds information automatically. So, for example, you can just observe the distribution, and it gives you a lot of information immediately. Because if you would be looking just into raw data in the table, that would be difficult to notice any obvious patterns in data. And also, as could be seen from before, it's very useful for applying all sorts of statistical tests. Also, within the Popmon, we have a so-called concept traffic lights, which is basically if our data falls into a green zone, it's all good. Yellow, we need to take care of it. And red, something is really outlying, and basically we have to immediately take a look at it. And we have implemented 2 ways of looking at it. One is a static way. So basically you can define those traffic lights in a more static way. So let's say if data falls into a range of, for example, between value for some feature between 10 and 100, you alert and you want to check the data. But what we also thought is when we have a lot of features, it's a bit hectic to define these static traffic light bounds for each of the features, and especially if there is a population shift, so data is changing over time. Maybe you want your data to allow to shift a little bit depending on your reference data. And so we came up with a more dynamic traffic light rules, which is based on standard score. So what we do, we compare each bin to the reference data. If you look at the formula for the standard score, we compare each bin to the expected value for that distribution, and we divide by standard deviation of that distribution. So in this case, you can see on the right plot that we compute the z-score for each bin, and based on our configurable traffic light bounds, which is here, everything what's below -2 or above 2 is red, and everything was below -1 and above 1 is yellow. So everything what falls into those, you would like to look at it. However, just for this demonstration purpose, we set these traffic light bounds so low. So this data is not so outlying, but for demonstration purposes, we set the traffic light bounds low to see that it actually outlies. But usually, the sensible traffic light bounds would be something between -7, -4, 4, and 7. So let's look at a more concrete case. So in this, in here, we basically, if you look at the right plot, here you can see medians for each week, or for example, for a year of data. So as the first bin represents a median for the week 1 for a specific feature. And here you can see how the median was changing over the year for that specific feature. And yeah, if we take this as a reference data, we can compute the mean value and standard deviation of this basically distribution, and apply this on the newly incoming data. So once again, by computing the z standard score, we can apply these traffic light bounds and see what is outlying on the new unseen test data. And the reference also can be chosen as we already seen in the previous example. So we could compare it to reference data, which is the train data. You can also compare it to self. So let's say we don't have any train data, but we have a lot of incoming data, and say we get it for a year. So we would like to compare each week to the full year. You could also do this the sliding. So for example, as we saw in the previous example, we were comparing each week to the previous week. We could say we compare 1 week to an average of last 10 weeks. So then we would have a rolling or sliding window. There's also expanding window. So compared to everything what happened in the past. So different traffic light comparisons are available here. We also have a prediction monitoring, which could be basically reduced to a data monitoring problem if you, for example, convert your probabilities, which is the output of your model, and you could track the distribution of those probabilities and see if the probability distributions are changing on your new unseen data. So, for example, if you in a bank, if you expect some part of companies going into default each month, let's say, and you track this distribution every month, if something is changing, if something has changed in your data distribution, for example, in this month in comparison to the previous month, you would like to check, you would like to see what happened in the data. Maybe there was some cleanup or something that was done from the business side, and maybe you would like to retrain your model because something has changed. Your model started evaluating your data in a bit different way. So once again, our package is not only for data scientists, it's also very valuable for data engineers. So for data scientists, it's great for data exploration. You can see data patterns, seasonality, you can find outliers, trends in data. It's also very valuable for early inspection of covariate shifts. But also for data engineers, it's very valuable because it allows to build data ingestion pipelines. So basically monitoring the incoming data to prevent drop in performance for your model. Also, stitching is available. So, for example, you have already some data that already is stored within this package, and then new data is incoming, for example, in batches, so over a certain period. So let's say we get new data coming in weeks, or let's say in a bunch of records. When you get 1,000 records, it's being stitched into this previous data and being compared to that data which is already in the pipeline, which is very useful because then you can see if this new data is outlying from the data that was seen before. Yeah, so from boring theoretical talk, let's maybe dive deeper into the code itself and see how easy it is to run a Popmon. So almost no initial configuration is needed. What you need is basically your data set. So in this case, we're using Pandas data frame. Spark data frame could be also used in this case. And what we do is we basically import our package. And by importing the Popmon, it extends the functionality of Pandas data frame. And it extends it with the function, in this case specifically PM stability report, which you can call later directly on the data frame. And as an output of this function, you get the report, which can be run directly in Jupyter Cell, which we'll show you in the demo. And you can even have it simpler. So if you have already your data frame ready, Pandas data frame, once again, you import your package, import Popmon package, and apply the same function. And also you can, by adding another function to file, you can easily store it in an HTML file and open it anytime on your laptop without need to run it in Jupyter Notebooks. And yeah, no internet traffic is also required because yeah, all the JavaScript files that are needed to run this report are being stored in this file. Yeah, so let's jump right into the demo. I'll show you the report that we get as an output from the Popmon. So here I've been using a Kaggle dataset, Kaggle flight dataset of the US in 2015, which has a bunch of different features like airtime for different flights, whether the flight was canceled, departure delayed, and these type of features. I have a subset of features that I've created myself. And to understand these plots, you can see that this is going from left to right. So this is all data for 2015. So we bin this data per 2 weeks. And basically we get, in this case, we see profiles. So in this case, we can see how many flights there were per that specific period. So in this case, per 2 weeks. So here we're looking at the feature airtime. And then we can see that, for example, on average, flights in different 2-week periods were around 120 minutes. Then you can also look at other features. Maybe something that would be a bit more interesting for us is the cancellations. So how many flights have been canceled during that period. And we can see that there were some spikes in the beginning of the year and the end of the year, which makes sense because that's a winter period. And there were way more cancellations if you compare it to the reference data. So you could see it is already outlying because it goes above the yellow and even red line for some of the 2 weeks. So these are the basic data profiles. We can also look at the comparisons, basically those statistical test comparisons. And we can see here a bunch of statistical tests that were described before, chi-squared, Pearson correlation. And if we look specifically at cancellations, we can see again some spikes in the beginning of the end of the year. If you feel like this is overwhelming to look at all these statistics, you can add these statistical tests yourself. You can also remove some of them because it might be too much. You can also look at aggregated features. So for example, here, aggregated traffic lights for those features. So if you look here at the canceled feature, you can see traffic lights for those specific time bins. So you can immediately zoom in and see like that there were a lot of outlying. Once again, our traffic light bounds are very liberal in this case. That's why we get a lot of red and yellow lights. But just for the demonstration purposes, you can set them as strict as you want. And then you have even more aggregation. So for example, here we have alerts for all the features without need to zoom in into specific metrics. We get all the green traffic lights for the specific feature. Let's look at again the canceled. We get all the green lights, all the red lights. We had 6 spike again in the same time bin, which was where we had a lot of cancellations. And then yeah, we can also look at the histograms of the specific feature. So in this case, we were looking at the flight data. So we have different airlines, the most popular airlines within in the USA, and then we can see how this data was changing. So the current week for this date, you compare it to the previous week and also to the reference data, which is basically different colors here. And how you might ask, how do you make this report yourself? So basically, in our GitHub repository, we have a tutorial. So in this case, you can click here, open in collab. So you don't even have to set up your own environment. And here we are running this in Google Colab. I already ran this, so we save a little bit of time here. Basically, as explained before, we import the Popmon package. We get some data, so some test data here, which is some random fake data, like with random features such as age, balance, company, etc. And then we apply basically this Popmon function on this data frame. We add some configuration, which is all described in the documentation for the package. But these are usually the most needed configuration settings, such as the time axis in your data, which can be also inferred automatically. We have also the time binning, so you can say every 2 weeks, every 1 week, every month. You can set it yourself. And also the features that you're interested in. Maybe you're not interested in the whole data frame, so basically you can specify here what you're interested in. You're getting report here directly in the Jupyter notebooks, very easy. But if you don't want to get the whole report, maybe you're just interested in the raw metrics itself, we're storing here the whole intermediate state. So basically, you can see different tables, the pandas tables, data frames, which are storing this intermediate information. Specifically here, as you can see, the profiles page, you can get exactly the same features and metrics if you look at this profiles key, and then you list keys, you get different features of the data, and then you can zoom in on specific feature of the data, in this case age, and get specific metrics for that feature, which was a mean standard deviation. And if you don't want to print the whole report, you can basically just print your own, you can plot your own plots as easy as this, just by using the computations that we have done with our package. So basically that's it from the demo perspective. You can also build your own more complicated pipelines. So in this case, we showed something that's maybe less customizable, but easy to use and out of the box. And yeah, you might be wondering, how do I create one myself, and how do I add maybe more custom functions to it? So in this case, on the top, you can see the modules that we import. We also initialize some configuration. Here you can see monitoring rules. So you can really do granular, you can define those monitoring rules in a granular way. You also, as also described before, you have a data store intermediate state. So in this case, it stores the outputs and inputs of the modules, which are important on top. And then we have a list of modules in the middle, which is basically here his splitter, which splits the whole year of data, for example, into weeks. Then we get his profiler, so it profiles those separate weeks into, gets the statistics of those weeks. Then we create a section, which is in this case called profiles, and create a report with report generator. So in this case, this is very simple pipeline, so we would get only one section, which we do call profiles. And then in a scikit way, we run this pipeline and get the output, the report, and we can print the stability report in JupyterCell. I also promised to explain one of the internal use cases that we had within ING. So here you can see one of the metrics that we can see, that we could see in the report, which is chi-squared. And here the feature was being compared every week to the previous week, and we were comparing different metrics. So in this case, I think it was count, and we could see or mean, and you could see in this case that there was a spike in September 2018. And after applying Popmon, we have noticed this, and we started addressing this. So we went to a data owner and asked what happened with the data. And apparently, after doing some investigation, we were told that the data source has been switched to a new data source. And when doing some tests, we have noticed that training our model on all data has a lower performance than training only on this new incoming data, the data from that point. So after doing some experiments, we have decided to use only the new data, and our training, training on the new data gave us way better performance. So this was a very good insight just by applying Popmon and on the data that we were using to train that model. So we have managed to improve the model performance without doing much of the feature engineering. So a short summary once again about Popmon. Yeah, we got it released in April 2020. Yeah, you should use Popmon to monitor the stability of a pandas or Spark dataset. It helps you automatically detect changes over time. Also alert based on static or dynamic business rules. It's very easy to extend. You can make your own data pipelines, as were presented before. You can add your implemented statistical tests, and they'll automatically show up in the report. Here I was focusing more on the 1D histograms, but 2D histograms are also possible. So yeah, feel free to play with it. And what future holds for us, as you can see, this is almost the end. So since there is a little delay in the presentation, it's time to ask questions. So the integration, what future holds for us in this case, we would like to integrate this with Amundsen, which is the data discovery platform, which was developed at Lyft, but in collaboration currently with ING. And by using Amundsen, we would like to use this on ING data quality pipelines. So, for example, we would be tracking all these, data changes over time automatically on our ingested data, which would be very powerful. And since we recently open sourced, a lot of new features are coming up, and we are open for ideas and contributions. So, for example, one of the features that we are adding now is this temporal view of the histogram. So, as you can see here on the bottom, we would like to represent histogram change over time, where the color is a bin count, and how do those bin counts are changing over time, which in this visual way you could see, for example, for the whole year of data very easily just by changing color, how those values were changing. And this provides a very good aggregated view on one feature over time. So we are adding these type of features, and we have much more ideas which should soon appear in the report. And we would also like to integrate this with our other packages such as Airflow and MLflow. Airflow specifically, so for example, we would have these reports being generated on the scheduled basis, or let's say every week or every 2 weeks, once again, depending how do you bin your data. And yeah, so that's it. And I have a question for you. Are you ready to give your data the attention it deserves? Thank you very much.
Yeah, so thanks a lot, Thomas, for your very nice presentation. And you got some compliments on your super nice slides. So in the chat we had already Q&A going on, because Dan was asking, do you have any plans to add extra statistical tests? One of our colleagues, Max, already explained that you already have multiple, which one you're thinking about, and Dan is just wondering. So can you elaborate on that? So do you have any plans to add extra statistical tests, etc.?
So the way we have done it, we have done it in we have done the implementation in such a way that users can add these statistical tests in a very easy way. So far we have implemented the Kolmogorov, Smirnov, and chi-square tests, and there are also quite some tests on the agenda, but yeah, we haven't prioritized yet. So I don't know if I can elaborate on this, but yeah, I guess maybe Max answered regarding this. I don't see the questions.
Yeah. Okay, thanks. Then we have a question from Feng Yun. Which tool do you use for your UI? Do you provide microservice for ING internal use?
So currently, we are generating these reports, which are HTML reports. So JavaScript is being used in the background. So basically, this file, as you can see here, it runs as a whole. It has HTML, JavaScript, and CSS. So if you're aware, within ING, we also have that platform, which runs Jupyter Lab notebooks. So since the output of this report is HTML file, it can be opened directly in the browser there. Also open Jupyter Lab cell. So yeah, basically it could be served and opened in any platform which supports browser view, I would say.
Hey, thanks. Then we have a question from Tim. So thanks for the talk and all the work on Popmon. Can you share a little bit more on the vision roadmap? For example, are there any plans for integrations with other libraries or for interactive plots?
So maybe on this plan in the future, because as we described, this is focusing on data monitoring. But I also described in the beginning that we would like to do performance monitoring. So we were looking how to integrate this with other packages such as Seldon and MLflow, which also look into model performance and deploying models. So we will be looking into the integration with that. Also, as I described, also in the future plans, it would be nice to combine this into Airflow DAGs, so make it an easy way for user to run this in a scheduled manner. So these are some of the initial plans, and also we have some visualization plans for the histograms themselves. As I showed in the report, and on the bottom we saw histograms, but it was a quite limited view because you can fit that many histograms in one plot to make it not understandable anymore. So we're looking into more creative ways how to show this. So also in this, what I showed is more temporal view with a lot of changing colors. So we would represent the histogram over time. So not in the basically 1D manner, but more 2D with the temporal axis, and by displaying different colors showing different bin counts, as I showed in this future slide. So we have different ideas for visualization as well. Basically we have a lot of ideas, limited time, so we are calling everyone to contribute. We would be very happy to share those ideas, and feel free to join.
Okay, thanks.
Thank you.
I think we have one last question from Jesse. What about non-numerical data? Does Popmon support that? Or do you first need to convert it into numerical features? We are building topic models, and we have a problem we face is when the new topics pop up.
So as I showed also in the demo, we had some also non-numerical features, like was categorical. So basically airline name. So that also works with the categorical features. Yes. It's let's put it in this way. So you can get more metrics and more basically more statistical tests on the numerical features. But yes, we support categorical features as well. Yeah.
Okay, thanks.
One more question.
Okay, no, Tim said I asked a question before your slide on future. So thanks for elaborating, Thomas.
Cool.
So I think this was it, right?
That was it. Well done.
Yes.
Okay, guys, thank you all so much for joining this. It's been really a hell of a ride for us because, of course, being on YouTube is super special. I want to thank, first of all, Daniel for his first presentation, Santiago, Thomas for the great talks, and Julien for helping us to make this happen on YouTube. We will share the slides of the speakers somehow. Next to that, you will, you help us a lot if you can respond to our survey, who will be sent to you this evening for the next future meetups that we will organize. And then the next meetup will be the data engineering meetup, which is on the 26th of August. And we will have 2 speakers from ING and an external one from another Dutch company, which is called, British company, which is called the Knights Analytics. So stay tuned. The next Data Science Meetup will be on October 8th, but you will find all the information online.
Yeah, so I think for the last, you can subscribe for this YouTube channel so you can be up to date about future events. And if you'd like to learn more about what we do in the field of data science or other IT topics, we have a very nice ING Tech Medium blog. So today, one of our data scientist colleagues, Nikki, her blog is being posted about the future role of data science. So if you want to learn more about what we do in tech and data science, please check it out. And for that, yeah, thanks a lot. And yeah, enjoy your evening, afternoon, whatever. And we hope to see you in August or in October. So thanks a lot.